Hi everyone, my name is Igor and I would like to introduce you to Filipp Gelman, who is a software engineer at Bloomberg in New York. And I also Googled him a little and it turns out that he is a 3D printing enthusiast. So Philip, maybe you can tell me if that's correct or not?
Yes, Igor, that's true. It's actually a fairly interesting piece of work with lots of computational geometry and pathfinding and that sorts of stuff. But instead about that, I'd like to focus more on templates and function overloading. So look
Yeah,
at the name of my presentation, unique pseudo function. Why do you think I called it that?
well, I suppose because it's unique and it looks like a function, but it's really not. I suppose you will tell us more about its usage during the talk, but how did you come up with such an obscure name in the first place?
Well, you got the reasons exactly right. It's kind of like a function, but not really. That's because it's an overload set. It's a whole bunch of functions all together in one object. So it kind of isn't, kind of isn't. And at the time I came up with this, I didn't know of a better name. Names are hard, right?
It is there. So shall we start with the presentation maybe?
Absolutely. So, hello everyone, I'm Philip, and I'd like to talk to you today about unique pseudo function. By the way, Bloomberg is a nice company to work at, and if you want to, you can go to that address and read more about it. So today I'll be talking to you about unique pseudo function. It's a class that combines a bunch of overloads of a call operator rather than just one. But that's actually a lie, because since I came up with that name, the C++ community has come up with a better one. It's called any invocable, which is a class like function, but it's move only, unique. And what I'll tell you is to add more overloads to that. So first I'll show you how it looks like and how you might be able to use any invocable. I'll try to tell you why I think this is cool, and I'll show you how to build one by first building a non-overloaded any invocable and then adding more overloads. And then, depending on time, we'll maybe look at the small object optimization and more fun stuff. Let's begin. So an overloaded any invocable, it's a class like Std function. That's a type-erased polymorphic container of callable objects. It's move only like any invocable, but unlike any invocable, it can have more than one overload of a call operator. And you can specify that by putting more than one function type in the template argument list, like I have 3 here. And before I show you how to use it, I'd like to take a few steps back and talk about callbacks. So I do lots of work with asynchronous libraries, and it's not uncommon for them to have an interface, but looks a little like this. I send an asynchronous request, and I provide a pointer to function that the library promises to invoke, eventually sometime later, when the response arrives. Now, this can be either an error, in which case I get an error code, or it can be a success, in which case I get a pointer to the response. And also I get forwarded the opaque data pointer that I passed in. This is fairly traditional C style, and it works, but it's not so great. I have to pack my state into this opaque pointer. With C++11, we can do better. We can instead pass a function object. And this is nice. It takes care of owning the state, takes care of lifetimes, but introduces a new problem, which is how many times will my state be copied? And with std function, I can't reason about that. I can't make any proofs at compile time. Send async might copy my state once, might copy my state more than once, although I hope it will be just once. And that's an even bigger problem if my state can't be even in principle, such as this lambda, which captures a unique pointer. If I try to pass this lambda to send async, I will get an error. Use of deleted function, copy constructor for lambda. Even though I don't actually copy the lambda at all, I move it. This happens because std function is copyable. It must allow eventual users of this object to use. So at construction time, when I try to construct this function with my lambda, it asks, okay, if somebody asks me to copy this later, how would I do it? Let me try instantiating some templates, and as it tries to do that, it fails. Because with lambda, it cannot be copied at all. Well, any invocable, which is a paper proposed for inclusion in C++, hopefully sometime soon, any invocable addresses this problem. It is like function, but it is not copyable, it's move only. And that solves the question of how many times my state will be copied. It won't, it will be only moved. But there is still one more problem here, and that is I need to handle success and failure kind of together, and I need to do a runtime dispatch on that. Can I do better? Well, if I instead pass an overload that handles either success or failure and handles them separately, then I can make that much better to do. And then I can pass a callback object like this one, with two overloads of a call operator that handle success and failure separately. And maybe these two objects can share some state. These two overloads can share some state, which would be much more awkward to do for passing two separate function objects. Or if I really want to, I can use Std Overload to combine a bunch of lambdas into one object. Std Overload, it's a class that combines a bunch of callable objects and basically exposes all of their overloads of a called operator, which is also a paper proposed for inclusion. But this Std Overload class, it does not erase the type. Here I'm using class template argument deduction to just sort of deduce what the type would be. But the full type name, it would be very big and ugly and have lambda names in it. To actually use such a thing directly, I would need to be a template. Or I could wrap it in some other type that erases the ugly templateness. And any invocable is exactly such a type. So I've shown you what any invocable is. I've shown you it. And next I'm going to show you how to build one. But my goal in showing you how to build one, it's not necessarily to say that this is the best way to build one, although I think it's a pretty good way. It is to show you techniques that are used to build it. And hopefully you will be able to use these techniques elsewhere in your own codebase. Also, I think it's very cool that here is a problem that we can use all sorts of C++ syntax to solve, like templates, partial specialization, variadics, fold expressions, enable ifs, finny concepts, function pointers, upcasts and downcasts, and multiple inheritance. It's going to be a lot of fun. And if we have time, I'm going to talk about whether such a thing, an overloaded any invocable, should be added to a standard library. So let's begin by building a regular, non-overloaded any invocable. It is a class template of one type name argument, and that type is a function type that has some return and some arguments. This is a move-only class with the special member functions you expect. But the interesting things about it are that it can be constructed from any type. We don't have to know upfront what it will be. It can be a lambda, it can be some adapter from functional, anything, as long as a thing can be invoked. And it has a call operator. You, the user of the any invocable, can invoke it with these arguments and get this return type out. And you don't have to know ahead of time how it was constructed. This is the runtime type erasure that this class provides. Build that by using virtual and an apps class. Here I have this base that has a pure virtual operator and a virtual destructor, and I'll have a unique pointer to set I'll use later. Next, I'm going to declare a derived class template that holds some t. It can be any t, different t's at runtime, but they all inherit from base. And that unique pointer below, it will point to some derived of some t. In the derived, I hold a t object, which is the one that I'll actually invoke later. And I override the call operator to invoke that object. So it can be a different t's at runtime, but they're all instantiations of this template. And remember, that unique pointer to base actually points to derived of some t. Using unique pointer in the implementation like this is nice. I can just default all the special member functions, and they'll do the right thing. Next, I have to implement the converting constructor, which is the one that actually takes an object t, and it creates a unique pointer to derived that holds that t. But if I write the constructor like this, there might be a problem. See, this constructor is not constrained. Just looking at the template in the signature, it takes any t. No rules, no restrictions. And this causes a problem if I try to overload other functions that take any invocable. Look at this example. I have a function named test that takes a string or an any invocable. It doesn't really matter which for this example. And I try to call test with hi. The problem is that hi, it's not a string nor an any invocable. It's a character array literal. So when the compiler tries to figure out which overload I mean to call, they're both viable. I get an error. Call of overloaded test is ambiguous because it might actually be an any invocable. Of course, if I were to actually try to construct any invocable from charconst 3, that would be a hard error because character arrays are not actually invocable. But at this stage of compilation, the compiler doesn't care about that yet. It's just trying to resolve which overload I mean. The fix is to constrain the constructor, to say this constructor is only present if the t is actually invocable with the arguments, and if such an invocation would produce a ret, or something implicitly convertible to. And it's very convenient that C++17 type traits includes a test for just this case. Now the constructor is constrained, and that second overload of test that takes any invocable, it's not viable. There's going to be a substitution failure because this condition is not met. That overload drops out, the compiler correctly picks the one that takes a string. I could equivalently, if I had access to C++20, use a requires expression here. But I'm sticking to C++17 for now, so we'll use enable if. And finally, there's one more thing left, which is to implement the call operator on the any invocable, which just forwards the arguments to the virtual call operator on the base, which is actually some derived of some t, which I don't know until runtime. Exactly described by this person at cppcon17. That's pretty good talk, I recommend it. Now it's time to think about adding more overloads. Remember, what we have is a base with a pure virtual call operator, but there's just one. I want to have more than one. I want to add a lot, one for each function type in the any invocable function argument list, template argument list. Can we build this? Well, that's a trick question. If we couldn't, I wouldn't be here telling you how. The better question is, how can we build this? And there are lots and lots of ways. For example, it might actually be possible to use multiple inheritance with a bunch of abstract base classes, each of which has one pure virtual call operator. And if you want, you can look up Dietmar Kohl, who came up with the idea for how to do that. But in my opinion, that's not so great. It's a little awkward. There's lots of recursive inheritance and variadics. And there could be a different way. In fact, there are lots of different ways. For example, Louis Dion talks about a few of them at cppcon17. and at C++ Now 2018. And this person from Google talks about a few more at CPPCon 2019. And this person from Bloomberg also talks about a few at CPPCon 2019. By the way, that's me. Hello. So today I'm going to tell you even more ways that this can be done. Let's look at what we have just now. Any invocable is a unique pointer to a base, which is actually derived. But that base-derived object, it has a hidden vtable inside. We don't see it, we don't put it there. The compiler puts it there for us, from us asking it to have virtual functions. And this vtable is a structure statically allocated somewhere in the program, but has the type info derived in some dynamic cast machinery, and basically a bunch of function pointers, one for every virtual function we asked the base to have. At least this is how it's implemented on basically any compiler that I use daily. And that's what we want this table of function pointers to have more function pointers in it, to have one for every overload we plan to add. Well, we can do this if we build the table ourselves. If we use template metaprogramming to build a struct which has the appropriate function pointers in it. How can we do that? How can we build this struct? Well, my approach is to try to decompose it into a bunch of smaller structs, but have just one function pointer inside. And that's what I call vtable entry. It's a template struct that takes one template argument, which is a function type. It defines an alias, pointer t, which is a pointer to member function that takes arguments and returns that return type. It also defines an alias for the trait, which asks, given some type t, is this t invocable with my arguments, and does that invocation return the correct type? Finally, each vtable entry holds a pointer of that type, a pointer to member function of the type pointer t. There's one more thing I need to do, and that is to take care of destruction. Remember that the base used to have a virtual destructor. That made the compiler do all sorts of convenient things for me to handle destruction and deletion of the actual derived. Well, now I need to do it myself. I need to store a pointer to what is, in effect, the destructor or the deleter. And finally, I have the vtable, which is the complete table of function pointers that combines all of them using multiple inputs. And it's constructible from all the appropriate pointer to member function types. One pointer t for the destruction, and one more for every overload that I plan to have, which is every element of the FNS Variadic pack. Next, by the way, all this vtable stuff, it's declared inside of the any invocable. Next, I need to change base. We're not relying on the compiler and not relying on virtual. Instead, we're doing it manually. So now base needs to actually have a reference to a vtable of the type that I just showed you. Next, we need to change derived. Previously, it would inherit from the base and just override some functions. But the structure was implicitly there. The compiler put one in for us. And there's one overridden call operator. But now we don't get that automatically, we need to do it manually. So first, I'll define a member function destroy, which is actually going to delete the derived, because they're always going to be heap allocated nude. So this function undoes that. Then, instead of having one overridden call operator, I'm going to have a call operator template, which takes whatever args and returns whatever vet. And I'm going to instantiate this template once for every overload in the surrounding any invocable. The fun thing about this instantiation is, unlike typically where we deduce the args and deduce the ret. No, here I will tell this template what args and what ret I want. And the implementation, as before, forwards the args to the object and returns the result. Now, this derived will also declare a const_expr inline static vtable object. That's the statically allocated vtable for this specific derived type. And this vtable will hold pointers to these destroy and call operator functions. So what I want to do is something like this. Put the address of the destroy function for this derived, and put the address of the call operator instantiated with every return and arguments types that correspond to the overloads that this any invocable wants to have. And the way to do that is by having a variadic pack expansion. So first, the destroy. The destroy is actually a pointer to a derived member function, but I can convert it to a pointer to base member function by a static cast. And I do the same for each call operator. Now notice here I don't specify explicitly what the args and what ret are every time. That static cast is what converts this address of what's still an unresolved overloaded call operator template. The static cast is what instantiates the template with the correct ret and arg for each element in FNS. But not just that, it also converts the pointer to derived member function into a pointer to base member function. You can think of this as almost the inverse or preemptive downcast that I would need to do to convert the base back to the correct kind of derived. I'm doing it here and baking that result into the pointer to member function type. All that's left is to take care of the constructor. Previously this would just construct the object, but now in addition it has to tell the base which vtable to use, which we do here. We construct the base with a reference to the static const_expr inline vtable object from this derived type. And of course then construct the object. Now any invocable, it declares the vtable entry, one for each FNS, the vtable destructor, the vtable, the base, and a template struct derived for whatever t it will eventually hold. The pointer is no longer a unique pointer, it's a raw pointer. And to take care of that properly, we can't default the special member functions anymore. We have to write them ourselves, which isn't too bad. So for the default construction, it's empty. The pointer is null. It doesn't point to anything. For the move constructor, I steal the pointer from this other any invocable and make it null. And now pointer is whatever other pointed to before, which could be null or could be not null. Move assignment, it's similar except I'd use the move swap idiom to swap the pointers around and destroy whatever this object used to point to before. And the destructor is what gets interesting. I can't just delete the pointer, because base is not virtual anymore, it doesn't have a virtual destructor. But what it does have is a vtable with a destroy member function that knows to do the correct downcast and delete the correct derived that this base actually is. So to delete the right thing, reach into the vtable, pull out the destroy function pointer, and call that pointer on the base to which pointer points. That is how I correctly delete the correct derived, if I have one. Which leaves us with the problem of the call operators on the top level any invocable. This is what I want. One call operator for every args and ret in FNS, which are function typer. So can we build this? And again, this is a trick question. Of course we can. I'll show you a few ways how we can build this. And what we actually want is this, right? A call operator that takes some args looks at the pointer, reaches into the vtable, looks at the vtable, and pulls out the correct function pointer to invoke, and then invokes that function pointer on the pointed to base. This is what we want. We want one of these for every overload that we eventually plan to have. And I don't have to split it apart like that. I can write it all in one expression. Just look at the pointer, look at the vtable, pull out the correct vtable entry's function pointer, and invoke on the pointed to base, forward that the arguments return the result. This is what I want. I want a copy of this for every overload. So how can I do that? Well, if we get reflection and code injection maybe someday, then this will be easy to do. But until then, I have to resort to more template tricks. Well, what if I had just one class, use multiple inheritance as before, to inherit from a bunch of structs, each of which have that call operator defined? This is the same thing as before. Look at the pointer, look at the vtable, pull out the correct function pointer, and invoke it. But there's a problem here. How is this invocable interface supposed to know where the pointer is? How to get the correct pointer from the any invocable? How is it supposed to know which any invocable it's a part of even? It's just taking care of one overload, and that any invocable can have lots. Well, the answer here is the curiously recurring template pattern, CRTP. Any invocable is actually a class template of two types. The first is a function type that tells this invocable interface which overload it's implementing, a specific ret and a specific set of args. The second type is the type of any invocable that inherits from this invocable interface. This is where the derived passes itself as a template argument to the base. This is where any invocable passes its own type as a template argument to the invocable interface from which it inherits. And now the definition changes only slightly. Now that I know which any invocable I'm the base of, I just need to downcast myself to that any invocable type. And then I know how to reach inside, how to grab a pointer, then how to grab a vtable, how to grab the correct vtable entry, and as before, I invoke that pointer on the base in the derived any invocable. Then in any invocable, I need to inherit from an invocable interface, one for every element in FNS, which are the function types that tell me what overloads I want to have. Then in the public interface, I need to inherit those call operators. And this is a variadic using statement that brings all those call operators from each invocable interface into any invocable. And that is how I achieve the effect of having one call operator for every element in FNS. It's as if I wrote that, except I'm inheriting it from a base. And this is nice. This lets me use the overload resolution that's built into the language to select the best closest match of the overloads any invocable supplies. The constructor needs to change only slightly. Remember that before we had one overload of the call operator, and we had to constrain the constructor to only accept t if it can be called just that way. Well, now we have many. Well, this is exactly why each vtable entry that the vtable in the base inherits from defines an isInvocable trait that checks whether some t is actually invocable according to the way that vtable entry wants it to be. And here I can just use a fold expression to check, are all of these constraints satisfied? And only if they are, is this constructor enabled. So that's what we have so far. And any invocable that is still move only, is constructible from any t which supports all the overloads we want to have, and can be invoked according to each of those overloads. This is a good time to pause and accept questions. Igor?
Yep. So we have one comment from the audience, from Yakov. So he says that on one of slides, you could remove const from your very long static inline constructor struct with table const, because constructor implies const already. Is it correct?
He's absolutely right. Absolutely correct.
Okay.
It's redundant.
Okay, cool.
Doesn't hurt. Doesn't help.
Okay, I also have a few questions about other slides. So how about we go to slide 53, where you declare the friend. I'm wondering if you can make this friend more explicit. So here you say that all invocable interfaces are friends of all n invocables. So maybe we can use some full specializations and kind of fold expressions here as well.
Maybe. When I was trying this by myself, and also when I tried it many years ago, there was a problem, and that is template friends can't be specialized. I can't say that only these partial specializations of a template are friends and those others aren't. I have to say that the whole template is a friend or not.
Agree,
but given that we're doing fold expressions here, it might be possible to say that these specific fold specializations of invocable interface are friends. It might be possible. I'd need to play with the exact syntax.
Okay, right. So another question is about your invocable interface trick. So here you declared, you inherited from a bunch of invocable interfaces, and inside each of them you specify an call operator. And I'm wondering, why do we even need this call operator? Because it's not even a template. It just call static as and calls every table entry. Why don't we just drop this struct altogether and instead implement a templated call operator inside any invocable itself? Because we have all the information, we know red, we know args, etc.
Thank you for asking. See, my first instinct when I was implementing an early version of this many years ago was to do exactly that. But that introduces a new problem. Imagine for a moment with me that I did it in any invocable, that I wrote template type name ... args, call operator of args, maybe ref. Now inside of this one template, I have to kind of figure out, well, which overload am I actually trying to call? And this isn't easy, because the args that I get passed in might not be an exact match for the overload that this any invocable supplies. For example, let's say this overload, it can take an int or a void star. And somebody tries to call me with a char. Well, the char is obviously implicitly convertible to an int, but it's not an exact match for the args of one of my overloads that I supply. So now in the definition of this template, I have to kind of figure out, well, what's the best match of the fixed set that I actually implement? And it's possible to do that, but it's very difficult. Lots of even uglier template syntax than I'm showing you here. But why do that? That's just overload resolution. That's what's built into the language. That's what the compiler can do for us. So this invocable interface, it's kind of a trick to arrange the expression of the class to leverage the built-in overload resolution in the language. Because the call operator here, it's not a template. It has a concrete signature and a concrete return type. And when I have the variadic using statement right here, these are also not a template. This tells the compiler it's a fixed set of call operators that this class exposes. You know exactly what they are. They're not templates. They have specific signatures. When somebody tries to invoke one, you pick the best match, according to the regular C++ overload resolution rules. That's why invocable interface needs to have a non-template call operator in it, to leverage that ability.
I see, yeah, that's indeed a really cool trick. Yeah, another few comments from the audience. So also Yakov suggests that it looks like you can replace unique pointer with a shared pointer, get a free ability to copy your any invocable, and also an easier type erasure.
That's true, but it's not exactly the same thing. See, if I have a shared pointer, then I can have lots of any invocables flying around my program that all reference to the same underlying state. So I've lost the uniqueness. Yes, it's now copyable, but I give up control. It's in fact even worse than std function. With std function, I at least know that each function object has its own separate copy of state. And now I have just kind of handles to this shared state that it's not great. And in my opinion, unique ownership, it's useful. It's a very useful property to be able to say for sure that only one owner of this state exists. At most one. And it can be used from at most one place. And can be moved around. Ownership can change from place to place, but always exactly one. And the last one destroys. That, in my opinion, is a useful property, which is why a shared pointer isn't exactly a solution.
Another question, so thank you for answering. Another question from the audience, from Denise. Can an invocable be used with plain functions, not functor objects? Denise is a little worried about delete used in the code.
I see. Okay. Well, if you pass an exact function pointer, not an overloaded function, but an actual exact function pointer, this will work. This will be a little inefficient. You'll have a heap allocated derived that holds a function pointer in it. And then the calling that will just forward things to the function pointer. So if you do that, it'll work. But that's not a good use for an overloaded any invocable. The problem is, if you try to pass it an address of an overloaded function, that will not work. Because the constructor, it's a T. And an overload set doesn't really have a type yet. It's just an expression that is convertible to some specific type, any of the possible overloads in that set, but I have to know where to convert it to. I can't just deduce that yet right here. And that's a problem in the language, that we can't just use address of overload set as its own concrete type. There are papers around that propose adding syntax for doing this in the language. And Vittorio Romeo has a cool short lightning talk at CVPCon from many years ago now. It's called You Have to Write It 3 Times, where he shows us how we can wrap such an overloaded function in a simple little lambda that has the effect of being invocable in all the ways that function pointer would be. So it's a problem, and right now there isn't a good built-in solution. I hope I've answered your question.
I hope so as well. It was quite an interesting answer. I have never thought of problems with Python overloading functions to any invocable myself. So I think that's all questions we have for now, and let's continue from slide 56, I guess.
Excellent, thank you. So that's what we have so far. We've built an any invocable, which is really just a pointer to some derived, which has a reference to some statically allocated vtable with the correct function pointers in it. So think about how many pointer jumps do we need to go through to actually invoke one of the overloads? Well, 1, 2, 3, depending on how you count. If you count the fact that the vtable actually holds function pointers, not function definitions, if you count that one, then the answer is 3, which might be fine or might not. And we can do a little better by putting a vtable instead of in the derived. We can move it to the base, which is good. Now there are fewer pointer jumps, and it's bad. The any invocable is bigger. But that's not exactly the problem that I want to talk to you about next. It's that one arrow pointing to the right. The derived object. That's always allocated on the heap. No matter how small or cheap to move it is, it's always on the heap somewhere over there. And that's not great because, well, heap allocations are potentially expensive. And maybe we don't want to do them when it's not absolutely necessary. Maybe we can leave some more room in any invocable to put small and simple objects right there in place as part of the object right there locally. Well, that's what I want to talk to you about next. That a lot of callable objects, a lot of lambdas really are small and cheap to move. They have no state, or they have very small state. Or maybe they're simple function object wrappers from functional, like less or plus. Those are cheap to move, really cheap. And heap allocations can be expensive, even compared to an indirect function call like the one we're doing. So next I'll show you ways to avoid that potentially. And I'll do that by introducing a buffer union. This is a simple class that's a union of a small character array and a void pointer. Now this class, it will define some functions. First of which is to ask, does some type t fit in this buffer? Could I in principle put it right here locally? And that function will be used to do different things than the other ones, like constructing some t, destroying some t, relocating some t to a different buffer, and actually invoking the contained t. Let's look at how those functions work. The first question I need to ask is, given some type t, would this t fit in the buffer? Well, how do I decide that? First, I need to check, well, does it fit into the buffer? If the size is too large, it can't fit. Next, I need to worry about alignment. There are types that have very strict alignment requirements. And if their requirements are stricter than that of this buffer, I can't keep them in a place, even if they would be small enough. I have to put them on the heap then. Next, so this buffer will be part of any invocable, and I want to be able to move between any invocables. I want it to be no-throw move constructible and no-throw destructible. And in order for that to be the case, then any object which is right here locally inside of a buffer needs to itself be no-throw move constructible and no-throw destructible. And if it's not, even if it would fit, and even if its alignment would be okay, if it's not no-throw movable, I have to put it on the heap and deal with pointers. So that's how I decide whether some type t fits. Next, I need to ask this buffer, please construct me this t object correctly, based on whether the t fits. Well, if it does fit, I can construct it locally by placement newing it inside the character array right here. And if it doesn't fit, I have to new it somewhere over there and save the pointer. Because that's what I have to do, it doesn't fit. Destroy does the reverse. Assume that I have some t that I previously constructed in this buffer. Now please destroy it. Well, if it fits, I must have constructed it by placement newing it here in the local character buffer. To destroy that, I need to cast a buffer and call the destructor explicitly. Otherwise, it did not fit, so I need to delete the pointer. Next, let's talk about relocation. I want to move the t that this buffer contains to some other buffer somewhere else, assuming that I hold a t right now. Well, if the t fit, then I must have put it in the buffer right here. So then I just need to construct a new t in that buffer over there, in dest's character buffer. And then I need to destroy my t because it's gone. My surrounding any invocable will be empty after this relocation, and that other any invocable that owns the destination buffer will own the t object. And in the other case, the t did not fit. I just need to counter. And that's okay, because after this, the current any invocable will become empty. It won't destroy or delete anything, it will not own anything. It will behave as if the buffer just holds garbage. And the other any invocable somewhere else, it will own this object, and it will eventually delete this pointer when the time comes. Finally, I need to know how to invoke the contained object. So assuming I previously constructed a t in this buffer and did not since destroy or relocate it, how can I invoke the contained t? Well, if it fits, it must be in the buffer right here, so I do the right kind of cast and invoke that and forward it the arguments. And if it doesn't fit, then it must be on the heap somewhere over there, and I do a slightly different kind of cast and invoke that. This is how I correctly invoke whatever t this buffer holds. Now, one thing to remember is buffer by itself does not enforce semantics, it does not do RAII. The user, the direct user of buffer, needs to be careful and consistent. We have to remember that first we construct a foo, and then we need to remember that it's actually a foo in there. And I need to specify the foo every time I invoke it with whatever I want to invoke it with. And eventually I need to remember to destroy the foo I put there. Now construct and destroy, they're syntax sugar that will do the right thing, but will figure out whether foo fit or not and do the right thing, either explicitly destroy it, or delete it, or cast an array, or cast a pointer, as long as I correctly tell it which foo it has. One more point is that relocation is a move and destroy operation. So if I construct a foo in buffer A and then relocate it into buffer B, buffer A is now empty. I must not destroy it because there's nothing there, just garbage. I must destroy the foo in buffer B. I have to remember that. But that's okay, because that's what any invocable is for. It makes sure that the contained buffer is used the right way. So to support this use case, I need to change vtable entry very slightly. Before, it used to hold pointers to base member functions. Now it holds pointers to derived member functions. These will be specific instantiations of buffer. It holds pointers to buffer member functions that are specific instantiations of invoke with the correct foo and the correct args and the correct ret. Otherwise, it's basically the same. The vtable detour, the struct that used to be responsible for deleting the right derived, it's now responsible for calling the right destroy on a buffer. That's what that pointer to member function is. It will point to a buffer destroy for the correct t that that buffer currently holds. And since I need to worry about moving objects between buffers that potentially hold objects right there, I can't just swap a pointer and be done. I might need to call a move constructor. And that's what vtable relocator does, vtable RLTOR. It holds a pointer to buffer member function to the right relocate function that I showed you a few slides ago. The vtable itself needs to change to account for this relocation. That's one more function pointer I need to have, in addition to the destruction and one entry for each overload that the surrounding any invocable needs to support. And one more thing, there's no more base, there's no more derived to have a vtable member variable. So now inside of any invocable, I need to declare a const express static inline vtable object for some type t, which I will instantiate later when I actually hold that t. So now any invocable, it has the vtable entry, vtable detour, vtable relocator, and the vtable. And the new template const exper variable, that is a vtable, a statically allocated vtable for some type t that I will eventually hold. It has a pointer to such a vtable, and instead of having raw pointer to base or void star, it has the buffer, the thing that either has space to hold small objects or is a pointer to big objects on the heap. The special member functions change very slightly. The default constructor is still pretty easy. If there is nothing, then the vtable pointer is null. I don't own anything, I don't do anything. The converting constructor changes slightly. Instead of newing a derived, I first remember, well, what t will I actually be owning? Let me save a pointer to its corresponding vtable. And then I ask the buffer, please construct me this t, which it will do by either placement newing it in right here in the character array, or by heap allocating on the heap as appropriate. The structure is very similar. Instead of calling a function pointer on the pointer to base, I reach into my vtable directly, pull out the destroy function, and invoke it on the buffer, which will in turn, based on which function it was, based on which t the buffer holds, will either explicitly call the destructor of the local object, or delete the pointer that points to an object on the heap. Moving becomes slightly different. I can no longer swap pointers around. I have to relocate the object. So the first thing I do is I steal the vtable pointer from the other any invocable. It's empty, no matter what, after I'm done, it's empty. But if it wasn't empty before, I need to also steal the object, which I do by calling the relocate function on its buffer and pass it my buffer as the destination. This will either move construct an object in my local buffer and destroy the object in that buffer, or steal that object's pointer. And for assignment it's similar, except if I previously owned something, I need to destroy that something before I relocate the other object on top. Invocable interface changes very slightly too. Before I could go self that pointer arrow vtable. Now I need to remember that actually the vtable is separate, and I have a buffer on which I need to invoke the functions in the vtable. But other than that slight change, invoking the functions on the buffer, it's about the same as before. So that's what we have. An any invocable with some space to store small objects, and still a pointer to a vtable that is statically allocated. And when the object is small, it's right there in place. And if the object is big, it's still somewhere else on the heap. But that's a pretty big win. And this might be a good opportunity to take more questions. Igor?
Yep. Hi, Philip. So yeah, actually, just as you was starting with your small object optimization part of the talk, we've got two questions which said that, oh, you should really do small object optimization. So I believe this was asked for, this was answered by last 20 minutes, which is really good. And I have a few questions of my own. So my first question is about extra copies and perfect forwardings that may or may not be present in your code. So for example, on slide 76, when you have an operator parenthesis, you say you always take arguments by value, thus making extra copies. So I'm wondering if that's correct, and if so, can it be optimized further maybe?
Thank you for asking. This is actually an interesting point that I've spent some time thinking about. The issue is this is tricky, and there are two different approaches here. So first, let me go back to the vtable entry. So relocator, vtable 4, it was earlier. Apologies, I actually don't memorize my slides. Here is the vtable entry. Now, see, if you look carefully here, this is actually a function pointer, a pointer to member function that takes args by r-value reference. But if you look at the invocable interface, that takes args by value. But that's actually misleading. And this needs to be done carefully. See, the thing is, this args in the invocable interface, it's not necessarily by value. It is explicitly specified by the template argument list to any invocable. So let's say I declare an any invocable that returns void and takes, well, let's say string const ref. In fact, that args is the string const ref. It's not deduced, it's not an argument type, it's specified by the template instantiation. So if the user of any invocable tells me that it should take string const ref, then args here, it's not value, it's string const ref. Preserves the category that was specified. So this call operator, in fact, takes exactly what they told me. It takes string const ref. And forward does the correct thing. It preserves the const refness and forwards that along. Now, on the other side, they could say take string by value, in which case this call operator would also take string by value. And this is an important distinction if they actually say R-value reference or mutable L-value reference. Let's say the user told me to take string mutable L-value reference. Well, that means that I have to take L-value references. I can't take R values, I can't take const references, only mutable L-value references. And I want to preserve that. And this does. The second case is if they told me take string R-value references. If they say any invocable that returns void and takes string R-value reference, then this args here will be string R-value reference. And this call operator will take only string R-value reference and forward that along. And you can't call this now with an L-value or a const reference anymore. It must be only an R-value. So that's preserved. But what if they tell me you take string value? No reference, no qualifiers, no R-value reference, no const, string by value. That's a different thing now. Now my function can take either an L-value reference or an R-value reference. And if this call operator is passed an R-value reference, then we'll move from it into a temporary object. And if it's passed an L-value reference, it's copied into a temporary object. So I want to preserve that. If a user tells me take by value, I preserve that behavior in the public interface. So my any invocable will correctly take by value and copy or move as appropriate. But this is only in the public interface. I want to preserve this behavior, and the cost is I need to now make extra copies or moves. But if we look at the vtable entry, right here, see, this is not args exactly. It's args ref. And this uses the reference collapsing rules in C++ to avoid more intermediate moves once I've gone past the public interface. So how this works is, if a user told me that I want L-value references, mutable L-value references only, args is mutable L-value reference to string. Well, what's an R-value reference to an L-value reference? Reference collapsing rules say that's an L-value reference. So that ref disappears, and this pointer to member function takes L-value references. So that's correct. Now the user tells me, no, I want it to be an R-value reference only. Now args is already an R-value reference, string R-value reference. Well, an R-value reference to an R-value reference, that's still an R-value reference. Now a pointer to member function that takes R-value reference, still correct. Now, what if the user tells me, no, not L-value reference, not R-value reference, but by value. I want you to take string by value. Args is just string, no ref qualifiers. Args ref is now a string R-value reference, which is good. At the public interface, at the invocable interface object, in that call operator, when I invoke that, I make a copy or a move into a temporary object, which I now have as the argument. When I then forward that temporary object to this function pointer, that's no copy or move anymore, because this function pointer takes the R-value reference. So I forward the R-value reference directly without moving again. I've avoided an extra intermediate move. And then when I eventually, I need to show you the buffer invoke right here. remember that in case the caller told me to take by value, this invoke right here actually takes by R-value reference. So args is actually an R-value reference to string if they told me to take string by value. It's also an R-value reference to string if they told me to take string by R-value reference. But if it's by value, it's an R-value reference as well. And when I forward it here, it's still an R-value reference. Now, if the underlying actual object actually takes strings by value, then I have to move it here again. I have to create a new temporary and move from the R-value reference into a temporary, which is actually a limitation in the language. The language C++ says that if you take something by value, then that is a distinct value from any other values in the program, which means if anytime a function takes something by value, I have to copy or move into that, unless the thing being passed is an actual R value or GR value, I forget the term. But there can't be another name for the object being passed by value, and here there is. So it's an extra move.
So essentially,
avoid
no
that.
matter. So yeah, so essentially, no matter what we do, if we use, if we wrap some objects and we pass by values, then we should do at least two moves: one on entrance and one when we actually invoke the underlying object. Yeah,
Right.
that sounds like a
Yes.
quite sad limitation. Okay,
I know.
nevertheless.
In fact, actually, at CPPCon 2020, somebody, Herb Sutter, it was Herb Sutter, he had a talk about exactly this thing. And he had interesting ideas for, instead of doing value qualification, values or references and constant R-value references, to do new kinds of qualifications in or out. And that would let the compiler sort of not worry about the distinctness of values anymore and optimize exactly this use case better. Maybe look up that talk, Herb Sutter, CPPCon 2020. But if you, the user, realize this and say, no, my function actually takes only R-value references, and the underlying lambda also takes only R-value references, then there's no moves at all. It's just forwarding R-value references all the way down. It's a limitation, yes.
Okay.
I hope I've answered that question.
Yeah, it's a great answer. Thank you. Yeah, and a small nitpick about slide 71. When you actually construct the vtable, can't we just use aggregate initialization instead of creating constructor ourselves?
Well, it's possible. The thing is that pointer T here, I don't know, maybe. I kind of like writing constructors because then I know that it takes only specific types. But
yeah,
it's
that
definitely
makes sense,
possible
yes.
that this can be aggregate.
Mm-hmm. Especially with all these changes for aggregate initialization between standards. Yeah.
Yeah.
Okay, I think that's
true.
I think that's all questions we have at the moment. Thank you.
All right. And well, that actually leaves me just enough time to talk about the thing I had planned to talk about next, which is, should something like this be standardized? And as a disclaimer, these are just my own personal opinions. Don't weigh them any more heavily than that. But the way I see the standard library as it currently exists, I actually don't think that something like any invocable, something like overloaded any invocable, should go in the standard right now. And I'll go over the reasons why that is. Well, first, the reason is there's already a paper for any invocable without overloads. And as far as I understand, it's basically ready to go. It was not included in C++20 for time. We just didn't have time to get to it from after all the other stuff. But it's fundamentally good. And trying to extend it now to support more overloads could delay it beyond C++23, which I don't want to do. I want my any invocable at least in C++23. But say we do that. We get any invocable without overloads in C++23. And can we add more overloads later? Well, we can't, because changing the template declaration changes the name mangling, and changing the name mangling changes the ABI, and we can't ever break the ABI, right? Because compatibility with previously compiled code is an important thing to do. But as a consequence of that, we're stuck with basically eternal choices like this. And well, what can we do? We can introduce maybe a new class with a slightly less clear name, but is just like any invocable, except you can add more overloads. But that's the situation we're in with lock guard versus scoped lock. Now, yes, scoped lock implements an algorithm to acquire things in different orders, but the single template argument of scoped lock, it's equivalent to a lock guard. And it would have been great if we could just extend lock guard to do the algorithm for multiple locks. But we can't because ABI, name mangling, and stability. So if you work for a company that has people on the committee, bring this up. This needs thinking about. Or maybe bring this up at the interview that we have during this conference sometime. The other reason that I don't think we should go in the standard library is that there is no 99% solution. I don't believe there is an implementation of this that is the best one 99% of the time. And one example is the buffer. See, I said that there is a character array here that's small and has some size. I didn't say how big it is. And I think that's because there is no best size for everyone. For any particular size, somebody will say this is too small or too big or something. And once we pick this value, it's baked into the ABI. Any invocable that uses this buffer must be n large. And if we change the n, we change the ABI, we change the definition of the struct, and that's bad because now things compiled with one size of any invocable get past things of different sizes of any invocable, and our code breaks. So ABI stability is a compromise. We can't do things like this so easily now. And the other reason is, well, the structure layout. I showed you before that we can have the vtable pointer in some heap allocated object, or we can have it right here as part of the any invocable, which has benefits and drawbacks. But there are lots of ways to do this, right? I can, instead of having a statically allocated vtable, I can put all the function pointers right there inside the any invocable. Now, this obviously has drawbacks. The struct is now much bigger, and it grows for every additional overload we want to add. It's big. But there's a benefit. The function pointers are right here. They're in the cache. They're local. I can get to them fast. And there are other benefits too, such as, let's say I want to construct a small any invocable from a big any invocable. Say I have an any invocable that takes void of args1, void of args2, void of args3, and I want to use it as the argument to a constructor for a smaller any invocable that just has args1 and args2. If there is an exact match, and the target is a strict subset of the source, all I need to do is just relocate the buffer to the destination and steal the correct function pointers from the source. And I can't do that with a statically allocated vtable because, well, there are lots of reasons. And I went more into those last year at CPPCon. But the point is this trade-off good for your code base? I can't know that. By definition, I can't know that. And neither can the standard library implementers. They can only pick an 80% solution or a 90% solution. They can't pick a 99% solution. But that's a question about the standard library, which has all of its limitations. But there are other popular libraries that could very well be or contain something like this any invocable. And some examples, Louis Dion's Dyno Library, which is a library for doing runtime polymorphism without virtual or requiring inheritance. It has the building blocks to build almost exactly the any invocable I showed you. And it could I got a lot of inspiration from his library and his talk, and it could contain a tool just like this one if it doesn't already. And Facebook's Poly library is a very similar kind of tool that comes with very similar kinds of ingredients. Google has their app sale library, which is a pretty good source for low-level stuff like this. And finally, Boost.org, Boost, the original home of the std function that we have in the standard today. I think that might be an excellent place for something like overloaded any invocable to live. Put it in Boost, get experience. Maybe there turns out to actually be a 99% good solution that can go in C++, Infinity, and beyond someday. And that's actually about it. I'm happy to take more questions now if there are any, in the few minutes we have left.
Yeah, so I would like to ask you some global questions about this data structure. So how would you compare performance of any invocable with, let's say, std function if we only take a single overload? Like, can we just plainly replace std function with any invocable everywhere in our programs?
Well, first of all, you can't do that because any invocable is move only. That's important. But putting that aside for a moment, if you just care about the memory usage and the data layout and the performance, it should be about the same. Like the small buffer, if you size it the same way, it would be basically equal. Now, I haven't measured because, well, there are lots of trade-offs. It doesn't have to be exactly like a function. We can put a vtable in place or in the heap, or we can put the function pointers inside, or we can change the size of a buffer. Now, for my actual use case at work, I definitely tuned this. I measured how it works for my code base and picked the trade-offs that work for me. And if you're doing this at your company, if you're actually writing this, measure for you. But it should not be any worse at worst. In fact, in the case where we have a small buffer optimization, and the object fits in the small buffer, and the compiler can also see the construction and the use of a function, then it can inline the whole thing out and just directly call what it actually has, and skip the construction and the destruction. If the compiler can see it, it can inline it. And if you're Clang, or at least sufficiently new versions of Clang with the right optimization settings, even if the object did not fit into the buffer if it was allocated on the heap, but the compiler can see the construction and the use and the destruction, it can elide that allocation and inline everything anyway. So in that respect, it's pretty nice. And if it's not inlined, if the compiler can't see it, it still has to go through the same function pointers, and the performance should not be really any different, depending on where you put the vtable and function pointers.
Thank you. Got it. Sounds promising.
Any more questions?
I don't think we have any more questions in the chat. So,
well, it looks like we have 2 minutes left, and this puts me in an awkward position. I have lots more slides, depending on how the time goes, where I talk about things like trivially relocatable, which is a thing that Arthur Dwyer talks about at C++ Now, and about which he has a paper. But the time we have left is really not enough to go into any more detail about this. But there's going to be an informal chat later, and if you're interested, we can talk there. Or maybe just go watch Arthur's talk. It's a very good talk, and he goes into a lot more details than I would have. But to briefly summarize, if such a thing were in the language, then I might be able to change any invocable very slightly to take advantage of it. This would make it much more efficient to move any invocables around, to keep them in vectors, and vector resizes would be much more efficient, and just benefits all around. So this would be really cool, and thanks to Arthur Dwyer for coming up with this idea and writing a paper about it and talking about it at C++ Now.
Okay, so maybe our hosts have some questions?
We'll have we'll hold it for maybe Zoom room where we can all join later. So I want to thank you very much for that interesting talk, and thank you, Igor, for joining the conversation. And so, if you want to discuss some more things, you can go to you can join a Zoom room via link in the Telegram chat. And I hope you see you there, guys. And so, thank you very much.
Thank you.
Thanks, everyone. And C++ is cool, isn't it? Like,
Absolutely,
that we
it is.
get all these different language features. Function pointers, multiple inheritance, variadic templates, variadic using statements, fold expressions, spin-A, upcasts, downcasts, CRTP, and we can use all of them at the same time to build such a tool.
Yeah, that's
Imagine
exactly
just what you can build.
Yeah, that's exactly a great tool. And let's talk it about later. We now have to finish our talk and move on. Thank you again.
Thank you. Bye.